Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC, IARE, Hyderabad. Yeah, today we will discussing about linear convolution using DFT and circle convolution using discrete Fourier transform. Here, in this case, we are recall that linear convolution is nothing but, so when the length of x of n, where here or it is given that x of 3, where x of 3 where x3 of n is equal to summation m is equal to minus infinity plus infinity x1 of n into x2 of n minus 1, when the length of the x1 of n, x1 of n, okay, that length of x1 of n, okay, and x2 of n, okay, or L and LP respectively. The length of x of 3 is L plus L plus P minus 1. Okay, so here it is mentioned L plus L plus P minus 1. Okay, so here, yeah, thus useful property is that the circular convolution of two finite length sequences with the lengths being L and P respectively is equal to linear convolution of the two point L, 2 point N, that N, capital N. So it is followed by that N is greater than or equal to L plus P minus 1. P minus 1. We know that that L plus, since that L plus P minus 1, we know. But this case, the useful property is that circular convolution of the two finite length sequences with the lengths being L and P is equal to linear convolution of the two n point sequences obtained by zero pairing. Okay, so here's this case with help of this. So another useful property is that we can perform circular convolution and see how many points remain the same as those of linear convolution. Within this, it is already considered that where x3 of n, where x3 of n is equal to that summation. Okay, the summation x1 of n, x1 of m, okay, into x2 of n minus m. With this is the length of when the length of x1 of n and x2 of n are L and P. If it is x1 is P, okay, where x1 of n is P, or x2 of, here it is x2 of n is P. Okay, here, so the useful property is that circular convolution of the two finite length sequence with the lengths L and P is equal to linear convolution of the two n point sequences obtained by the zero pairing. Okay, another useful property is that we can perform the circular convolution and see how many points remain the same as those of linear convolution. So within this case, so when P, P, the P value, P less than L, and L point circular convolution is performed. Here with the P less than L, we are right to concentrate on that circular convolution is performed. Okay, right to verify that. And the first P minus The first p minus 1. The first p minus 1. Okay, and L point circular convolution. L point circular convolution. Okay, L point circular convolution is performed. The first p minus 1 points are corrupted by the circulation, and the remaining points from the n is equal to that remaining points are where n is equal to p minus 1 to p minus 1 to what you call n is equal to L minus 1. Okay, like this, the linear convolution using that DFT, how it is varies when p less than L and L point circular convolution is performed. The first p minus n points are corrupted by circulation, and the remaining points from the n is equal to p minus 1 to n is equal to L minus 1. Okay, like this. So linear convolution or circular convolution will appear. So recall this linear convolution property. The linear convolution property, you know that where what you call x3 of n is equal to x1 of n, where x1 of n convolved. Okay, convolved what you call x2 of n. Okay, so with this the convolution property is that what do you call with this x3 e power j omega is equal to x1 of e power j omega into x2 to e power j omega. Okay, if the necessary discrete time Fourier transform, okay, is exist if x1 of n is length is x1 of n length is n1, and x2 of n length is n2. This is n2. Then x3 of n will be what you call will be length is n3. Okay, so therefore that n3, where n3 is equal to n1 plus n2 minus 1. Okay, this for the DFT, we have to consider the DFT, discrete Fourier transform. The DFT, we have the circular convolution property x3 of n. x3 of n is equal to x1 of n circular convolution x2 of n. So that we will write to x3 of n is equal to x1 of k, x2 of k equal to 0, 1, 2, 3 up to n minus 1. Where x1 of n convolved with circular convolution with x2 of n is equal to summation k equal to 0 to n minus 1, x1 of k into x2 of n minus k into n, the summation k equal to 0 to n minus 1, x1 of n minus k and x2 of n. Yeah, note that x1 of n and x2 of n must have the same length. N is equal to n1 is equal to n2. The expected result will be appeared. So result x3 of n will also be length capital N. Okay, like this we have to recollect this linear convolution property. The linear convolution with the DFT, discrete Fourier transform. Suppose we want to compute x3 of n is equal to x1 of n convolved with x2 of n. We would compute the discrete time Fourier transforms of x1 of n and x2 of n. First x1 of n and x2 of n. Okay, take their product and then compute the inverse discrete Fourier transform to get x3 of n. That is where x3 of n is equal to, it is written that where x3 of n, where x3 of n is equal to inverse discrete time Fourier transform. You can consider that all DFT x1 of n, the product into discrete time Fourier transform of x2 of n. So this x1 of n is the inverse discrete time Fourier transform product with this discrete time Fourier transform x2 of n. Okay, so compute that the discrete time Fourier transform of x1 of n and x2 of n, take their product and then compute the inverse discrete Fourier transform to get x3 of n. Okay, so what if we want to use the discrete time Fourier transform to compute the linear convolution instead? We know x3 of n is equal to this value. Like, how do we know this? Once we arrive at this, how to calculate this, how to compute the discrete time Fourier transform with the help of x1 of n and x2 of n. Take their product and then compute this inverse discrete time Fourier transform to get x3 of n. So will not work because this performs circular convolution. Okay, so like this, they have right to distinguish the linear convolution and the circular convolution with help of what you call discrete time Fourier transform and inverse discrete Fourier transform. So how it is used? We want to use that discrete time Fourier transform to compute linear convolution. Instead of, we know if that x3 of n is equal to inverse discrete Fourier transform, okay, of DFT x1 of n into DFT x2 of n. It will not work because this performs a circular convolution. What is that circular convolution? A circular convolution of the two finite length sequences, like s3 of n is equal to the summation m equal to 0 to n minus 1 x1 of n, okay, and x2 of n minus m into n. With this, x3 of n is equal to the summation m equal to 0 to n minus 1 x2 of m x1 of n minus n. Okay, here it is x1 of m and x2 of m. Okay, with the, here it is x2, here it is x1. Okay, with this, so consider the m versus x2 of m. M value, that m value is, it is assigned that m value, initially that m is equal to 0, 1, 2, 3 and so on up to what you call n or n minus 1, where it is, where m is equal to 0, 1, 2, 3, so on, n minus 1. Okay, with reference to the m value and x2 of m, and with reference to that m versus with the x2 of what you call 0 minus m into n and so on. We use that all interval 0 less than or equal to m less than or equal to n minus 1, one case, and if it is x2 of 1 minus m, okay, and to what you call into n, that interval 0 less than or equal to m less than or equal to n minus 1, and finally that where x3 of n, that x3 of n is equal to what you call x1 of n with the circular convolution, it is followed by n. With this product, with the circular convolution of this x1 of n, circular convolution with x2 of n. Okay, like this, we have to verify this particular value. The circular convolution of the two rectangular pulses where L is equal to n is equal to 6. How it is appear, the circular convolution of 2 rectangle pulses, L equal to n is equal to 6. After that, we write to verify DFT of each sequences. Because of the linear circle convolution with the discrete time Fourier transform, how we are analyzing, how we are computing with this. So after that, the multiplication of the DFT, discrete Fourier transform, the circle conveys 2 rectangle pulses, how it is varies. So after that, and the inverse discrete Fourier transform. For this, where so x1 of n is equal to x2 of n is equal to 1. Here that 1, 0, 0 less than or equal to n less than or equal to L minus 1. 0 else. Next, DFT of the sequence. DFT of each sequence. DFT of each sequence is followed by x1 of n is equal to x1 of k is equal to x2 of k is equal to summation n is equal to 0, 0 to capital N minus 1 into e power minus j 2 pi by capital N into k and n is equal to n, k equal to 0, 0 else. You have to follow this DFT of each sequence. Next, multiplication of the DFT, discrete Fourier transform. Here, x3 of k is equal to x1 of k into here x3 of k is equal to x1 of k. This is the x1 of k into x2 of k. Is also equal to that n square, where k equal to 0, 0 else. Next step is inverse of the DFT, discrete Fourier transform. Here, inverse of discrete Fourier transform. Here it is x3 of n is equal to what do you call n 0 less than or equal to n less than or equal to n minus 1. Okay, 0. Okay, else. This is the inverse discrete Fourier transform. So graphical representation of this, we have to verify that n versus n versus x1 of n. Okay, so here it is 1. If it is 1, so the origin is 0 and 1 and up to n. Next one is xn versus x2 of n. x2 of n is n, this n into k equal to 0. Okay, so like this 0 elsewhere and x3, similarly x3 of n. So example of this, we can augment these zeros to each sequence where L is equal to 2, N is equal to 12. Okay, here with this, the DFT, discrete Fourier transform each sequence. Okay, so how it is appear, we can augment these zeros to each sequence. L is equal to 2, N is equal to 12. Now that what the multiplication of the DFT, discrete Fourier transform. x1 of k is equal to x2 of k is equal to 1 minus e power minus j 2 pi L into k by capital N by 1 minus e power j 2 pi k by n. Okay. Next, multiplication x3 of k is equal to 1 minus e power minus j 2 pi L into k by n by 1 minus e power minus j 2 pi k by n whole square. Okay, so easily you can distinguish this the DFT of this sequence x1 of k, and after multiplication of the DFT x3 of k, we'll evaluate, we will calculate. So where n versus x1 of n, like this, n initially 0, L to n, and n versus x1 of n. So after that, n versus x2 of n. Okay, after that n versus x2 of n, x2 of minus n and 0 less than or equal to n less than or equal to n minus 1, and so on. Okay, next of finally. Okay, if x equal to, we know that if x equal to wx, where here it is x, okay, capital X equal to wx, where small x is equal to 1 by n, so that the weighting function w into x. Okay, with this DFT analysis equation, the equation is x of k is equal to wx. Inverse DFT synthesis equation x equal to 1 by n w into x. So let's recap our notations. The notations are here. X of t is equal, t is the, where t is the real, x is the continuous, time domain and real function. It is specified x of t. T is the real, that x is the continuous, x is the time domain, x is the real function. Similar case where x of k is the integer, where k is the integer and x is discrete time, time domain and real function. Next, x of z, where z is complex, where x is z domain, what you call z transform, z domain complex function. Next, x of f, where f is real, that x is equal to discrete time Fourier transform, frequency domain and complex function. Okay, where x of I, where I is the integer, where x equal to discrete time Fourier transform. So here we write to expect that all what you call frequency domain and the complex function. Okay, frequency domain and complex function. So by using this all notation, it's a recap our notations are easily can recognize that all in terms of the time domain and frequency domain variations. Okay, this example where that weighting function w is equal to here j power 0, minus j power 0, here all are minus j 0, minus j 0, minus j power 0, minus j power 0, and j power 0, and j power what you call 1, 2, 3, and 0. So the 0, next 2, 4, 6, next 0, what you call 3, 6, and 9. These are the weighting function. So because of where x is equal to wx, so here it is 4, 3 plus j, 3, 2 and 3 minus j3. Order of the DFT is n square because it is the n by n matrix or multiplication. You see that where x equal to 3 minus 1, 0, 2. Okay. So using this all are, so we try to compute that all what you call fast DFT computation, faster DFT computation. Okay, so take the advantage of this symmetry and the periodicity of the complex exponential, that what you call Trudel factor. So we will expect that all faster discrete Fourier transform computation. Take the advantages of the symmetry and periodicity of the complex exponential, that w n e power minus j 2 pi by capital N. So what is the symmetry and the periodicity? Here it is. So where symmetry is the wn k of n minus n is equal to wn minus k is equal to wn bn. If it is the periodicity, wn kn is equal to wn k of n plus n is equal to wn k plus n into n. Note that the two lengths n by 2 discrete Fourier transform take the less computation than one length DFT, that is followed by 2 into n by 2 square less than n square. So using this faster discrete Fourier transform computations, we can consider we can follow the symmetry and periodicity. We can consider what you call. We will expect that fastest or faster by using this DFT computation, whether it is using the complexity or somewhat number of expressions, or go on substituting this n value and k value, somewhat it is. So not that much faster. So the time we can consider we require this aeronautical algorithms. By using the algorithms that exploit computational saving. Why it is computation is saving? Computations are very high because of where based on the n value, the k is ready to substitute, small it is also go on substitute. Here also n is ready to decide, the k value you have to substitute, and small is also substitute. After that, each and every weighting function are twiddle factor. So somewhat we will expect that our computations are very high. You have to compress that one. You have to save that all computation time. Algorithms that exploit computational savings are collectively called fast Fourier transform. FFT, fast Fourier transform. Okay. Now, discrete Fourier transform applications. We have relevant, but in terms of the linear convolution and circular convolution with the help of DFT only. Discrete Fourier transform, just we have discussed. Based on this linear circular convolution. So now it is effect with this DFT. We will consider that all discrete Fourier transform applications. The applications are many applications demand the processing of signals in frequency domain. So one is the analysis of the signal frequency. Now they will analyze signal frequency, periodicity, somewhat the energy, as well as the power spectrum can be analyzed in the frequency domain. Once we are having that all convolution sum, linear convolution, circular convolution with the help of the DFT, the applications are changes. The applications are many. The analysis of signal frequency, periodicity, energy, and power spectrum can be analyzed in the frequency domain. So frequency analysis of the discrete time signals is usually and most conveniently performed in digital signal processors. This is a major application. Okay, so the applications the DFT, discrete Fourier transform. So the discrete Fourier transform is involved. Okay, one is spectral analysis. Another one is convolution of the signal. Next application is partial differential equations. So after that, the multiplication of the large integers. So data compression, that time we require the DFT, like the distal image processing, we require this type of DFTs. Data is compression. Okay, so like this, the time domain, frequency domain transformation, the time domain is kind of what you call continuous periodic, continuous non-periodic, and discrete non-periodic and discrete periodic. So using this all time domain, the same one is in the frequency domain, it will appear discrete non-periodic. Okay, so this case the continuous non-periodic only. Next discrete non-periodic, and the frequency domain continuous non-periodic. Okay, the time how it is coming, this all time domain to frequency domain, or the time domain and frequency, the transforms are used here. Fourier, by using the Fourier series, we are ready to observe this one. So we are ready to analyze this time domain and frequency domain. Similar case, the time, if you are applying the Fourier transform for the continuous non-periodic or the continuous non-periodic variation in both the time domain and the frequency domain. Now discrete non-periodic. So, and continuous non-periodic frequency and the time domain. Sequence Fourier transform is using this one, it will appear. Next, discrete Fourier transform, our case, discrete Fourier transform. So, in the frequency domain, there is a discrete periodic. In time domain, there is a discrete period. Both are same. Okay, like this, we are ready to use this type of applications. Okay, with the help of linear convolution or subtle convolution with help of DFT. So discrete Fourier transform applications many, but major applications are what you call spectral analysis, convolution of the signals, and partial differential equation, multiplication of the large integers, and data compression.
Like, share and subscribe. Hit the bell icon for more updates.